Hello and welcome. Here we are in lecture 17. So remember when we last spoke, and it's been quite a few lectures, right? Because we had our great guest talk on Monday by Kevin talking about formal. Then we had project group meetings. Then we had a holiday. Then we had a guest lecture from Professor Jose Renau talking about PyRope. It's been a while since it's been me. But since the last time you saw me, remember we kind of shifting gears going from very code-heavy content to more general hardware design, physical optimization kind of concerns. And so in particular today, we're going to shift gears a little bit more and talk about delay. So far in this course, we've been concerning ourselves with designing generators, focusing on reuse, parameterizability, various aspects of code, and that kind of stuff. But we haven't really thought about the hardware costs of what we're doing, right? And so one of those hardware costs is delay, right? What's the performance? And so today we're going to talk about that just from a more general sense, so folks who have less of a hardware background, more familiar with the physical constraints. But even those who are more familiar with physical constraints, we'll talk about what can we do about delay, right? So let's get to it. Okay, so like I said, we're going to talk about both what causes delay in our circuits and how can we try to reduce it. Okay, so actually there will be a code example at the very end, so I might as well open a notebook now. There we go. Okay, so unlike in our simulations, when we actually run things in real hardware, things take time, right? Nothing's instantaneous. And so there is some amount of delay for a logic gate to perform an operation. That's the gate delay. And of course, the more inputs the logic gate has, the more complicated our arithmetic function is performing is, it takes more time, right? So for example, you might hear this term fan-in, which is the number of inputs. A high fan-in gate usually takes longer, right? If there's more inputs, there's more circuits need to interact, that's going to take more time. There's also a delay, not just from the logic itself, but the wiring between the logic elements, right? The wire delay, the time it takes to move signals between things. And so depending on the context, wire delay can be very small or really big. So for example, in a well-optimized ASIC design, your wiring delay may be a small fraction, right? You have logic gates that are very close to each other. The wires are very short. Things are running really fast. By contrast, sometimes FPGA designs, the wiring delay can easily be 4x or even 10x the logic delay, right? You have some things that are farther apart, and because of the FPGA nature, you can't really easily move them closer together, and so you have to eat a lot of wiring delay. And so that takes some time. In terms of delay, for wiring, it's both a function of not only how far it's going, but also how many things it's driving. So if you have what's called high fan-out, as you have many outputs you're driving from the same source, that can also impact delay. Okay, so when we talk about delay, usually we talk about it in some sort of unit, right, to make it more concrete. And so the natural thing for many people would be, oh, let's talk about it in terms of time, right? So the delay is the time, so we're talking time units. And because these are really fast circuits, these are really small time units, right? To talk about things in terms of nanoseconds, they're actually really more likely picoseconds nowadays when it comes to gate delays, right? So if your circuit's running at several gigahertz, that means your clock period's below a nanosecond. So that means you're already in a picosecond domain. So picoseconds is kind of a very natural unit for that. One unit you may not have seen is something called FO4, or fan-out of 4, which is actually an interesting thing that came from the research literature. And that is that as we keep changing technology, we have 32 nanometer process, 22 nanometer process, 14 nanometer process, 10 nanometer process, keep changing transistor size and making more and more denser and denser. The same circuit manufacture of a smaller and smaller process tends to go faster, right? That's kind of one of the things we hope for Moore's law. And so as a result, a design from 20 years ago has a certain latency or a certain delay. The design from today has a certain delay. And you might say, oh my gosh, based on delays, the one from today looks a lot lower. But the question is that due to the design or is that due to the process? Well, the changes in process are so dramatic that usually it's due to process. And so one way to try to ignore the impacts of process, something called fan-out, like I said, is technology independent metric where we try to have this unit that's related to the design, not related to the implementation of technology. So normally if I say, oh yes, this is a 100 nanosecond or 100 picosecond delay, that's usually referring to a specific implementation. Okay, I'm using this particular logic bandwidth for this particular technology at this voltage and this operating point. FO4, fan-out of 4, is taking a much more technology agnostic point of view, right? So normally the way you drive it is for a given technology, you see how long does it take for a single inverter to drive 4 inverters, right? That's a fan-out of 4. And so given that number, you kind of have this number, and so that way, whenever you have a delay in this technology, you can divide it by that number, and you can turn this into fan out of 4 units. And so as a result, you can talk about a processor or some other circuit in terms of its delay in terms of fan out of 4 units. So for example, from Wikipedia, the Intel Pentium 4 back, now nearly 20 years ago was a 16.3 FO4. Now that at first may not be a very familiar number. Perhaps the number to the left is more familiar. 3.4 gigahertz, right? That's a pretty high clock rate. That's actually not too different than what we have today. So you're sitting here going, wait a second. Okay, so 20 years ago, we had 3.4 gigahertz. Today, you buy a CPU. It may be 3.4 gigahertz. I don't believe this laptop CPU is actually listed that high on its base frequency. It probably can turbo that high, but maybe not for its base frequency. So what's going on? What's going on is, in that time period, transistors have gone a heck of a lot smaller and faster. But the clock frequency seems to be nearly the same. So if you look at what happens within a given clock cycle, this one's actually going through, I'm pointing at my current laptop, it's going through a lot more layers of logic, right? And so turns out this design is maybe about the lowest FO4 you have in the processor. So this processor in front of me might be like a 20 or 30 FO4 design. In terms of that means it has much more logic it's going through. Because the transistors are faster, we don't necessarily see a lower clock rate or reduced clock frequency. That's kind of what's going on. So when you talk to people in architecture, and especially in industry who are doing hardcore physical design optimization, to kind of get a sense for how aggressively to push in the clock, rather than talking about frequency, they talk about FO4. Okay, this is a design we're trying to shoot for sub 20 FO4. That means you really have a carefully optimized pipeline. You're really going fast. For some research projects where we have a hard time reaching high clock rate in FPGA, I shudder to figure out what FO4 is. It's probably in the hundreds, right? Like we have a very long, complicated combinational logic path, and so it's a long delay path, right? And so that happens. And so, yeah, there's a little side here to see this FO4 metric. We haven't seen it before. Cool. Okay, so why are we so concerned with delay? Well, your delay is going to set how fast the circuit operates, right? So we talked about how in these, synchronous digital systems, of course, we use a clock to synchronize everything. So everything kind of goes the same beat, the same clock to do state transitions. And well, how fast can that clock run? Now, in 2023, one of the biggest limits for how fast a clock can run is the power, right? Otherwise, it's too fast, runs too much power. But independent of power, how fast you can run is determine what produces the correct solution, right? And so you actually can't go arbitrarily fast. You only can go as fast as the slowest element, right? And the slowest element is the critical path, which sets, it's a straggler that sets how fast you can run things, right? And so however fast your clock is switching, it needs to switch at a rate slower than the critical path delay, right? And so we often hear people talk about longer or shorter paths, talking about how much time it takes for these things, but that time is often strongly correlated with, distance or more logic elements. So in this example, hypothetically, we're saying, yes, this path that goes through 3 gates is going to be a critical path for this particular circuit over here, right? And for whatever reason, we're saying that, this path takes longer than perhaps going through here. But yes, that's maybe this wire is longer, and that's the reason why it's slower. Okay, so as a designer can reduce my critical path, I can help the design overall, right? I can, number one, if I have a shorter critical path, I can have a shorter clock period, and a shorter clock period means I can increase my clock frequency and go faster. That's cool. So you can improve performance. The other one, which is a little bit more subtle, is I can save energy, right? So let's talk about that one. So if I reduce my critical path delay, but I don't change my clock frequency, so in other words, I keep the same performance, but if I have a less delay, what it actually can do is actually can turn the voltage down on my circuit. If you turn down the voltage on your circuit, it's going to go slower, but it's going to take less power. So in other words, for the same performance point with a shorter critical path, same performance means same frequency. I can turn down the voltage so the critical path delay now just barely matches the clock period, but it's shorter originally in FO4. That's going to let me save power, right? And so this is kind of what it comes together. And so you often really want to optimize the critical paths, right? Whether it be for power, performance, or both, you really want to get a handle on this. And so, like I said, this example I gave just right now, in the same technology family, changing the voltage, you're going to change the delay in terms of picoseconds or nanoseconds. You're not going to change the FO4. because FO4 is relative to inverters, right? So if you lower your voltage, it's also lower for the inverters using for the same comparison point. And so it said, so to improve your critical path, you're going to have to improve your FO4. Okay, so how might we go about doing this? Well, one tool that's now taken for granted, maybe it's worth appreciating the world without it, is something called static timing analysis, which is, or STA for short, is a CAD tool that looks at your design. It's aware of the delays for the logic gates, it's aware of the delays for the wiring, and it does its best to estimate how well things will work timing-wise, right? And so, it depends on the models. There's different levels of sophistication to the models. The reason why we use the word static timing analysis is this referring to the fact we're doing this agnostic to the inputs, just looking at the circuit in general. You can imagine doing a dynamic timing analysis where you're doing detailed simulations and seeing how certain transitions from 0 to 1, 1 to 0 impact certain things. Also okay, but usually STA is sufficient now that STA is so well done. And we're kind of concerned with the worst case. So STA is going to say, okay, given the worst case delay for this logic gate and the worst case delay for this other logic gate, what's the worst case delay for this toggling? And so depending when you run STA, sometimes you run it after you synthesize logic gates, but perhaps before you have any wiring delays, so you actually don't know how long these wiring delays are. Or perhaps you run it after you're done placing routing, you also have wiring delays. In terms of these numbers, I'm not going to go into too much detail. This is just one simple forward and backward algorithm where let's say you're trying to figure out the critical path. So from all these circuits here to the other end, right? I think we just had a second ago. Well, in green, we have the various delays. Okay, so for this XOR gate takes 8 time units, which is longer than 4 for an OR 2 for an AND. Okay. There's some amount of time delays for these wires. Maybe they're longer or shorter, or more circuitous paths. And so you kind of see what's happening, right? So for example, the blue is the input arrival time, and the orange is the output arrival time. So you see, for example, that originally all these inputs are available at time 0, perhaps on a new clock cycle when things are changing. Okay, they go through this initial wire delay, and then they arrive wherever they're going. So for example, this has a wire delay of 1, so it arrives here at time 1. Or it has a wire delay of 3, so it arrives here at time 3. Then we add on the gate delay. So for example, over here it's just pretty simple. Okay, it comes at time 1, gate delay of 4, time 5. Now over here it's a little bit more interesting because the inputs arrive at different times, right? So one arrives earlier, right away at times 3. This one comes at times 10 because it came through this gate, this wiring path, and this other delay. So it took a little longer to get here. If we're concerning ourselves with the worst case behavior, we're going to take the max of these two, right? So then we're going to take the 10 and then add 2 to get the outputs available at 12, right? Now, it could be a case based on the input values that when this value arrives later, it doesn't change the case of the output, right? For this analysis, we don't care. For analysis, we care only about the worst case, right? So we want to know, in the worst case, most adversarial case, it's like big O in CS theory complexity. What's the worst case? And you kind of can propagate it through. Okay, so the output changes at time 12, sure. Add on 2 more for wiring delay. And so finally reach over here, we can see, okay, once again, take the max. So the latest arriving input's here. And we see that, oh yes, it takes 23 time units to get here. Now, if you're curious what the critical path is, well, you crawl backwards. And you can go see, okay, well, this is the latest arriving one. So far it's this path. This is the latest arriving one, so it's this path. And oh, wait, these are the same, so it's actually both. And I believe that corresponds to the prior slide. Perfect, okay. So there you go. As you can see with critical paths, it's not necessarily exactly one path. It could be splitting, it could be merging. It's just whatever has the highest latency. Okay, so that's just the background delay. Now when you as a designer get involved and your boss tells you, yeah, we need to ship a product at a certain frequency, and you're like, what are we at right now? Oh shucks, we are not there. What happens, right? So for example, if you run static timing analysis on your design, there's a large number of paths. There's actually a combinatorial explosion number of paths, but there's a large number of paths you need to check. They'll have a certain delay. Turns out, fortunately, most paths are actually pretty short, so you're okay. But there's usually a long tail, right, in terms of how long the delay is. Unless they have a certain clock period you're trying to target, well, all these paths that are longer than that need to be dealt with, right? Otherwise, you can't run the frequency. You have to run at the longest path. So your critical path frequency is over here. You have to run that critical path latency over here. And so you're going to figure out a way to speed up these paths, right? So what you're going to do is you're going to run static time analysis. You're going to identify your paths that don't, quote unquote, meet timing. They aren't as fast as you want for the target period. and figure out a way to intervene. And so normally this is a very time-consuming thing. This is where the time goes. I mentioned a second ago about this, talking about your design in terms of FO4, what you're targeting. If you have a lax frequency target, hard design is a lot easier than the very aggressive thing. If you want to run a super, 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 super low FO4, super high frequency, you spend a lot of time optimizing paths. But if you don't care and you want to run at 200 megahertz on a brand new process, hard design is not as hard. You can do things a lot easier. But okay, let's say you're trying to optimize these things. Well, you got to go through these paths and figure out what it takes, right? And depending on these paths, in many cases, the tools themselves can optimize these paths for you. But after the tools have optimized it, there's still going to be some paths left you have to go ahead and fix, right? And so what do? Well, you find the longest path, make it somehow shorter. Great. You use over and over and over again. And so all these paths that are too long, well, with a lot of effort, you got them to be just fast enough. So thus, they're going to be all right here. So you get this kind of hilarious little distribution where you have this little spike at the end where everything's kind of just barely meeting timing. And great. And so, well, if everything's less than target period, you've reached your target clock rate and you're done. Now, the thing to be aware of is then if your boss comes back for next year and says, make this design go 10% faster, you're like, okay, great, we have a new process. And he says, no. Then you have a lot of work to do because now there's a lot of paths you need to make go faster again, right? They're all still kind of your critical path. So you can see after this optimization, all these paths we managed to move to the left. So like I said, there could typically be multiple critical paths, which happens a lot in hardware designs, right? After you've done a lot of optimizations, you really push frequency, you're going to end up with multiple critical paths, and that's okay. But just be aware of that for next year's design. If you don't have a process help, you're going to have a hard time optimizing it. Okay, so when it comes to fixing this delay or fixing a critical path, what can you do? Well, one of my themes for this course, of course, has been let tools do the work, or not just let tools do the work, make tools do the work. And so it's worth thinking about what tools can do and what humans can do and figure out the best synergy, right? And so this kind of stuff, there is so much research, not just academically, but also in shipped commercial tools, that this is something that's, some of this kind of path kind of optimization stuff, the tools can do really well. So for example, they're really, really good at giving complex logic functions, identifying common terms, factoring the logic, changing logic depths. They are extremely good at that. They can simplify logic. They can also make trade-offs where, you know what, they can synthesize using one logic gate and realize, oh wait, this is too slow. I need to resynthesize that using a faster logic gate. The tools can do that, right? They can do that really well. So there's some trade-offs in terms of area and power. They can try and navigate that. They can often do that really, really well. The thing they can't do is they can't change the semantics of the design, right? So if you have Verilog that says this is a certain behavior, and that Verilog, for example, could be produced by Chisel, it's obligated to produce hardware that mimics that behavior. So, if the result comes on cycle 2, it has to make a circuit that produces the result on cycle 2. It can't make a circuit that has more cycles, right? It can't make a design that takes 4 cycles rather than 2. That's not something tools can do normally. So what can the designer do? The designer works at architecture level, right? So they can change the design. They can change the semantics. They can say, you know what? In order to reach this clock period, I'm going to need to pipeline deeper. So I'm going to change the cycle level behavior, right? That's something they can do. They can also do major architectural changes. You're like, oh my gosh, I need to radically rethink this design. So remember maybe in 220 we talked about out-of-order processors and the shift from a data in ROB to a unified physical register file design, right? It's a big architectural change, right? And so you have to kind of, as a designer, recognize opportunity for that and do that, right? And so if you make these big changes, then the tools micro-optimize, right? Now, maybe 30 years ago, you spent a lot of time actually looking at every single logic gate and reconsidering each logic gate. Like I said, in 2023, the tools can do that. Usually, if there's a path the tools can't optimize, it's because you need to architecturally change it. Or you need to decide, you know what, this is too much logic between these two registers, and you figure out a way to break it up or something. Cool. Questions so far? Okay, so how do you fix that? Well, the one that's kind of alluded to indirectly and maybe more explicit is pipelining. So of course, pipelining is, if you have a lot of logic between two registers, this could potentially be a long delay, right? A lot of gates, a lot of wires. And so that could be your critical path, right? And so if you put a register in the middle of that, well, you have a shorter critical path. Now, you've changed the semantics of your design, right? This data comes out over here one cycle later because it goes through more registers in the middle. And depending on the nature of this logic, it may not be easy to break it up, right? But the point is you've done this, right? So from a high-level architecture point of view, what have I done? Well, You're still doing the same computation, still doing the same logic gates. You're just adding registers in there, so it goes less distance per clock cycle. In order to do this, one of the key requirements, you have to have the parallelism in your design, right? In other words, when I go from this design to the one below, I have one thing in flight here. Now I actually have two things in flight. I have one here and one here. So depending on semantics of your computation, that may be trivial and maybe not a problem at all. Other times that is a problem, right? For example, on a processor CPU, remember from your architecture courses, remember how much time I spent talking about pipeline CPU and the various hazards pipeline introduces, and that's because we have multiple instructions in flight. But some other workloads, there's plenty of parallelism you don't mind, right? If I have this pixel versus another pixel, if there's no data dependencies, sure, I can have more pixels in flight, not a problem. And so, okay, cool, we're gonna put registers in there to reduce critical paths. Sounds simple. The next question you might have is, well, where do you put registers, right? Where should they go? Now, a lot of times as an architect, you might think conceptually, oh yeah, I'm doing this operation and then this other operation, right? So it's kind of a semantic, or conceptual idea of where the register should go. That's not always the best place to put it in practice, right? Because you really want to put it in a place in practice that actually balances the delays. And so, well, how do you balance the delays? That can be tricky and time consuming. This is why one of these things where, once again, you want tool assistance, right? Because you can put it one place and then run a tool and see what happens. And remember, when you put it in one place, tools are going to synthesize the logic on both sides. They're going to place and route all the logic. And then you move it, the register over one gate, and then it actually resynthesizes, replaces, reroutes. So actually it's going to perhaps even be non-monotonic in ways causing changes and delays. It's going to be very labor and time intensive, right? Where you keep tweaking things and watching what happens. And so naturally the question is, well, can we somehow automate this, make tools do the work? And that's the next slide, retiming. So this is technology that was developed originally in the 80s and became productized in the 90s. I believe this actually was Charles Licenson's PhD thesis, where he actually won the ACM Doctoral Dissertation Award. And so he figured out, you know what, why not have tools move registers around, right? So if I have the semantics of my design such that I have the parallelism and have the registers, usually it's possible to move registers. So he's not adding registers, he's not changing the semantics, he's just moving around in the design, right? So in other words, maybe I have a long conventional path here and a couple registers. Well, I can go ahead and have the tools move this register for me, and they can figure out what's the best place to put it based on the latencies and delays. Now, that's in theory how retiming is supposed to work. Depending on which CAD tools you're using, varying level of success. From my own personal experience, I found that the expensive commercial ASIC CAD tools do this phenomenally well. They are just aces at this. They can do it forward or backwards, meaning put registers on both ends. It figures it out, no problem. They crush it. One of my personal frustrations has been Xilinx Vivato's ability to, or I should say inability to do this well. It doesn't do this very well automatically, even though they keep talking about it. And what's disappointing is actually if you use Xilinx's prior FPGA tool, ICE, it actually did it pretty well. And so there's actually a regression in performance from ICE to Vivato, and Vivato's been around now for, 8 years, and it still seems to not be fixed. And so it depends on the CAD tool. For the open source CAD flows, I haven't tried them as much for this particular optimization. I believe some of them can do it. Who knows how effective it is. But when you're doing this as a designer, like I said, the goal is, once again, make tools do the work. So your goal as a designer is to recognize, oh wait, I have a long combinational path. I want it to be pipelined. I don't know where registers should go. So I should just put registers at the end of my design and let the tools using retiming figure out where they should go for me. That's the idea. That's the goal. Like I said, depending on the CAD tools you're using, it doesn't always go according to plan. Sometimes some CAD tools want the things at the end. Other CAD tools want registers in the front, and they'll only move them forward or only move them backwards depending on the tool. But definitely worth checking out. Okay, so if you try to do retiming in Chisel, how should you do that? Well, it's actually a great thing for a generator. You can just add a FIFO at the end. Not even a full FIFO. It's actually just a pipe module, which is actually just the shift register. So it's not even the ability to really stall or anything. It's just registers connected in the sequence. And so if you registers in sequence, you can put a parameter. So you can set this to parameterized depth. And then you can basically put an arbitrary latency for your module, right? So you say, oh yeah, based on technology I'm using, I'll have this be pipeline depth of 3. And trust the CAD tools to optimize and retime this to get it right. Maybe you want to target a higher clock rate. You change your pipeline depth to 5. Once again, let the CAD tools move these registers around it, right? So this is Like I said, the ideal case is what you want, and for ASIC tools, it usually works pretty well. Fortunately for FPGA tools, not quite as reliable, but that's where we are. Cool. Okay. Well, given that, one other thing you might commonly try to improve clock frequency is recognizing, okay, I have a lot of logic. Can I perhaps solve the same problem arithmetically with a shallower depth to have less latency, right? And so like I said, once again, understand what CAD tools can and can't do. They can't change observable behavior, right? If your RTL tells it has to have a certain logic function implemented, it needs to implement a function to provide the same logical behavior. Now, they can do synthesis tricks, optimizations to simplify the logic and do other things to it, but it needs to behave the same, right? And so if you're not careful, sometimes you make something that's hard for the tools to optimize, and they're kind of stuck with it, and they have a hard time. Other times, especially with Chisel, actually, the emitted Verilog from Chisel may seem really inefficient, but the CAD tools recognize what it's doing, and they can optimize that for you really well. So for example, like if you do a VEC in Chisel, when it gets turned into Verilog, it's actually turned into a mux per element. Basically, if I have like an 8-element vector or 8-element VEC, it's like, hey, is this element 0? No. Is this element 1? No. Is this element 2? No. It's like this linear, unbalanced tree of muxes seems really bad, but most CAD tools realize, oh wait, I see what's going on. Do the right thing, have one big mux, and it's handled. Cool. So when it comes to us as designers, like I said, number one, before you do any optimization, run things through the tools, analyze it, make sure what you think is a problem is actually a problem. But if it turns out it is a problem, you want to go ahead and optimize this, let's go see what you can do. And so one case that comes up a lot of times, the generators, you have something that's arbitrary. And because it's arbitrary, you may have like a linear thing set up. If something grows linearly, maybe it's a for loop, maybe it's recursion, but to handle n things, you kind of just do things in a row, right? And perhaps one way to improve that, number one, you could pipeline it. Another way is you could perhaps, instead of doing something linearly, you could do it with a tree. And like I said, whenever you optimize anything, hardware or software, make sure the thing you're optimizing is actually make a difference, right? It may turn out that this hardware you're really worried about isn't on a critical path, in which case this optimization is not needed, right? Don't do this unless you need to. Alternatively, maybe this is a problem. This could be a problem, but the tools are optimizing it just fine, right? They're actually handling it okay, in which case, once again, don't spend effort until you know for sure you need it, right? So make tools do the work, but use the tools to scout and make sure you have a problem before you go ahead as a human and try and fix it. Okay, so first example of trying to reduce the depth of this kind of problematic path, what we can do is to go through and, okay, let's say in this example, try and do a reduction, right? So we have n objects, we want to add them together. So maybe by simple Chisel generator, just add them together linearly. And, that's depth n, or technically n minus 1, right? If you do things in a tree fashion, we can reduce the depth to log n, right? That's pretty cool. Now, you may say, oh, great, I can go from this to this, right? Why can't the tools do that? Well, depending on what you're doing, they either can or they can't. So if this is a logic function you're reducing, they can probably do it, right? If these are OR gates, it's probably know what to do, and it's probably do that just fine. If these are addition, it actually can't do that change because it breaks the semantics, right? Because doing things in this linear order versus in this tree order, the accumulations are different orders, right? In this case, we're adding n minus 1, input n minus 1 to the partial sum. As opposed to over here, we're adding input n minus 1 to input n minus 2 before going over. So depending on the possibilities of things like overflow and such like that, the addition is not going to be associative. Addition is non-associative in this case. Then the tools can't change the order, right? So they had to be more cautious. Okay, but let's say we as humans decide we want to do a tree-style reduction. So let's try and do a tree-style reduction. Okay, well, in this case, to make this problem really simple, rather than doing this arbitrary addition, we're actually going to do something called pop count, which is another way of saying counting number of ones in a binary number, right? So our binary number in this case is going to be a sequence of bools. Remember, bool's the Chisel type, and this is a Scala collection of them. Okay, so we want to figure out how many ones are true inside here, right? So one way of doing this is, what if I do this recursively, right? So I say, hey, if you give me an empty collection, well, that's going to be 0, 1s, okay. And if it's a non-empty collection, well, I'm going to take whatever the first one is and then add it to the remainder, right, the tail. So you see the recursion, we have, n things, n minus 1 things, go all the way down and go through it. Okay, so we go ahead and put this inside of a module, count ones to be our, pop count implementation. We can go ahead and run this and then look at the Verilog. It is what we expected. It's a little bit confusing to look at because of the bit truncations, or say the bit extensions, I should say. So because a bool is 1 bit, if you add 2 bools and you have truncating addition, the result's also going to be 1 bit. But of course, if we have n bits, there could be, the result could be a number up to n, which is going to need log n bits to represent that, right? So you need to grow the result sum to kind of handle that information. That's why we're using the non-truncating addition. This is the growing addition. And so thus, in the Verilog, it's initially growing the inputs before it starts adding on to things. But the key thing is there's 3 additions in sequence. Okay. So now if we try to do this with a tree, we can do this a little differently, right? So instead of doing 1 element, we could have a shorter recursion depth, right? Each level of the recursion, okay, if I only have 1 thing to do, we're matching based on the size, how many things we have left to go. So if I have 0 things to go, okay, it's 0. If I have 1 thing to go, I can just do the head element. If I have 2 or more things, I can just split the list in half and give 1 half to one call to this function and the other half to the other call to this function. That's doing that tree behavior, right? Now, the inside of these parentheses, this is a little bit of Scala finesse. So for collection, the take operation, so this is being called in a collection L, will take however many objects you say it is from the beginning, versus the drop will ignore that many from the beginning, right? So in other words, take combined with drop, given the same collection, the same argument, that's what you're picking at 2 halves. So you have the 2 halves, and you call the recursive function on each half. If we go ahead and run this and see how our Verilog looks, looking a lot cleaner. In this case, the chisel is able to do a lot better job where even though we're still requesting it to do this non-truncating addition, because of the things are already properly sized, it's doing 2 1-bit things added together and then capturing the second bit right away. We still have 3 additions. We actually haven't changed the number of additions in this case. But it is, much shallower, right? We're only going 1 addition, 2 additions rather than all 3 in a row. And you can make this, of course, bigger if we wanted. Sure. And yeah, we can see it's growing. The depth is growing logarithmically, right? We can see how the final result uses T2. T2 uses the 2 inputs. So it's, only 1 level more. Okay. And then naturally you may wonder, okay, well, what about the chisel, built-in one, which is in Chisel util, once again, use what's already there. Well, that's already there. And there you have it. So that one's, I can maybe just make this 4 so it's more clear. Yeah, they also use a tree-based thing. So cool. So that was an example of us optimizing for delay. Cool. Any questions? Okay, well, we flew through this material because no one had any questions. Maybe everyone's already all physical design experts. To orient everybody into class, if you saw last night's Slack messages, a few things, right? So we posted lab 6 as formal. For that lab, you're primarily just writing a handful of assertions. So you're probably going to spend more time wrapping your head around what the module does and what the assertion should do. When you actually see the code, it might be really short. That's kind of expected. But the thing is, why I mentioned this in the lecture is that this one's not going to be auto-graded, or not going to be well auto-graded. Just because you have a high score on the auto doesn't mean you're guaranteed to get the highest score in the final thing, because the staff needs to go and actually manually grade it because it's the assertion. So if your assertion doesn't check aggressively enough, it's not going to get full points. But try aggressively. Our instructions try to very clearly explain what assertion should check for. If you have any concerns or questions, please Slack us or come to office hours. And then, of course, the other thing to mention is our major. If we're doing formal, you might be wondering how to remember formal. Well, we had Kevin's guest lecture on Monday. We linked to the video, so he requested to use the public version of his talk from last year, which we did. But he's also okay for you folks using the internal recording, which is available on YouTube if you want to watch me saying a lot on the microphone. And then for the project course, it's the big thing you're working on. Intermediate deadline is coming up in less than a week, right? And so the intermediate deadline, we want to see a repo where you have some code that does something. Doesn't need to do the entire project, just something. Perhaps imagine us as the staff. We're going to go ahead and read your README, and README will say, go ahead and clone this, and then run SPT tests. SPT tests is do some sort of initial proof of concept of something, right? So go ahead and do that. And of course, yeah, once again, for projects, come talk to us as staff, myself, you're on paying, office hours, Slack, we're here to help. Cool. Any last questions? That's it. I guess we're done very, very early today. Yeah, okay.